All right, so what we're going to do is we're going to talk about the formula for the derivatives of logarithms. And the first part of this notes should be fairly straightforward in that it is going to, shall we say, review log properties because they're so important. I thought I would throw a quick review in of these to start with. So reminding you, logs are simply inverses of the exponentials. You know that you can switch from log base b or base b exponential into a log base b. Technically, the behind the scenes of switching is because if I take log base b of b to the x of both sides, what happens to the log base b and the base b exponential? They cancel out because they are inverses, and that's how you are switching from one form to the other. It also works the other way. That went from b to the x into log form. If I want to go the other way, what I'm doing is I am taking each of these sides of the equation that are here, and I am applying a base b exponential to both sides. So if I have log base b of x equals x, if I apply the base b to both sides, these would cancel out, and x equals, you didn't realize I just wrote an x, y. Okay? So inverse properties of logarithms. So you should be able to switch. You should remember that logarithms are nothing more than an exponent. That is all they're talking about. If I have log base 4 of 16 equals 2, I'm saying the exponent I put on 4 to get a result of 16 is 2. Logs are exponents, so that's all you have to remember. All right, so take a moment and quickly evaluate each of these. Now, when you're evaluating these, you can either just do it in your head, or if it helps you to rewrite this, rewrite it in exponent form. What I'm asking for is saying 2 to what power x equals 8, if that helps you to rewrite it in exponent form. Or you just basically go, what exponent do I put on a base of 2 to get 8? What's your answer? 3. What exponent do I put on 3 to get 1 over 81? Negative 4, right? So you need a negative to make the fraction flip. And then what exponent do I put on 16 to get 4? 1/2. That if you have to go from a big base to a smaller number, you had to do a root of some sort when you're doing it. All right, so log properties. Sketching the graphs. The base is what is going to tell us whether it's exponential growth or decay. If you have the base greater than 1, then it is a growth for exponential. If the base is greater than 1, how do you get the inverse of the log graph? How do you get the log graph from the exponential? How do you get any inverse from its original function's graph? Flip it over, y equals x. So visualize the exponential, which is doing this, the growth, and then flip it over the line y equals x, and you should be able to kind of quickly sketch every log graph that is the inverse of a growth exponential. The important thing is all exponential functions have a horizontal asymptote at y equals 0. All log graphs have a vertical asymptote at x equal to 0. Okay. Also tells us the domain of the log graphs, 0 to infinity, because it's the range of the exponential. Likewise, if I come over here and I'm doing the base between 0 and 1, that is the inverse of a decay exponential. So you want to imagine the decay and imagine flipping the decay over. Okay. And if it helps, what do you think the decay is going to be related? How's it going to be related back to this one? How was the exponential decay related to the exponential growth? What transformation would you have done? Flipped it horizontally, so if it helps you to get the decay growth there, instead of flipping horizontally, you're going to flip the growth log vertically. And so if that helps you to kind of see that the graph is going to be coming down and going like this for your inverse of your decay graphs. And likewise, this also has a vertical asymptote right at the x equal to 0. All right, the special logs that you are supposed to remember from last year, whenever we have the natural log, that is always understood to be a base e, we just don't write it. If you don't write a base, we understand that it is the common log, which is base 10. And x is called the argument, just for lack of something else, the input, the argument, so that I can refer to it. Right? Properties of limits. All right? Oh, do you remember limits? Yes. We come back to them, just remind you, it's the end behavior of logarithms. This is composition. Do you remember limits of composition? What's the first thing we have to figure out? Where does the highest power, because you're going to figure out where the inside is going to go. The inside is polynomial. I'm not going to write it down. I'm just going to do it, because we should be able to, at this point, answer this question in our head. As x goes to infinity, where does x squared minus x go? It goes to infinity. So I look at the inside first, and that's going to infinity. And that becomes the new limit right there. You figure out where the inside goes, and then that gets filled in there. In this example, it does happen to be the same thing, but that's just coincidental. And then we figure out of the outside function, and where is the log function going as x goes to infinity? It's going to infinity. It's going to infinity very slowly because it's concave down, but it is always increasing. Logs do not have horizontal asymptotes. They're just very flat as you go out because their rate of growth is very small. But they do keep going to infinity. It just takes them a long time to get there. All right, same thing. Let's come over here. I'm approaching 9 from the right. We're going to do the same thing. We're going to figure out where the inside function goes. As you go to a 9 from the right, where does x minus 9 go? They go to 0. Now, because of the log, and I know that there's no left side, I do need to make sure, how am I going to 0? If I'm on right of 9, that's a big 9. That's bigger than 9, right? So bigger than 9 minus 9 is always a positive number, so it's approaching 0 from the positive side, so I make that positive. And then I take the log base 2 of the limit on the outside function. And then as you approach 0 from the right, where is a base 2, which is an inverse of an exponential growth, going? Going where? Negative infinity, because those growth curves go down. So that is going to be negative infinity. If it helps, the growth curves always increase, but the decay curves always decrease for logarithms, if it helps you remember which one is which. All right, same thing. We're going to do the inside function first. We are going to approach pi over 2 on the tangent function. What's happening at pi over 2 on the tangent function? You have a vertical asymptote. So if I am, is that a minus on your notes? Is it from the left? So if I quickly just come up here and sketch my tangent function, right, just a little rough sketch. If I am left of pi over 2, where is the tangent function going? Infinity. So this becomes the limit as x goes to infinity of the log of x. And where is log going as x goes to infinity? It's going to infinity. Again, this is the inverse of an exponential growth, so it is always increasing, so it is going to infinity. All right, our last one. The limit as x approaches 0 from the right of cosine of x. Where is cosine going? Going to 1. I'm still going to think about left or right because I'd like to know how is it going to 1? From above or below? From below, which would be from the less than side, from the negative. So it would be left of 1 of log of x, which actually did not matter in this case because how do I calculate this limit? What do we know about log functions on parentheses 0 to infinity? They are continuous, so how do I evaluate a limit of any number that happens to be in the domain? You just plug it in because it's continuous there. So this becomes the log of 1. You will not leave logs just like you don't leave trig. Log of 1 you can evaluate. What exponent do I put on a base of 10 to get 1? 0. So this answer is 0. Okay? So nice little review of limits. All right, before we get into calculus, domains of log functions, 0 to infinity. We cannot have 0, we cannot have negative numbers. So to find the domain of g of x, you have to take whatever the argument is, and we know that it has to be greater than 0. The minute that I see that that's a quadratic inequality, I have to use critical points and a sign chart. Factor it. This is x minus 2, x minus 1. What are my critical points? What makes it 0? 2 and 1. I put them on my sign chart. 1, 2, 0, 0. I figure out when I am positive or negative. It's a quadratic with a positive lead coefficient, so plus, minus, plus. So which part do I want to keep in the domain? The positives. So from here to here, do not include that. From here to there. So my domain is going to be equal to negative infinity to 1 and then 2 to infinity. So that tells me automatically that the log function is not going to be differentiable on 1, 2, or any number in between 1 and 2 because it's not going to be continuous. Log functions are continuous on their domains. All right, I'm going to leave this for you to do for homework in the interest of time, so we're going to skip that. And I'm going to leave you to do that for homework because that's just more practice. I just thought I wanted to do the domain because I need to get to calculus. We're still on properties. Lord, logs. It would be so helpful if y'all just learn this so I don't have to keep repeating myself over and over and over again. The log of a product is the sum of the logs. Log of a quotient is the difference. If you have a power here, you can move it to the front. You know, all of those. Can I just wave my hands and say, know your log properties? I am going to leave you to do for homework, example 5, because that's pre-calc, review. Because I want to, in my last 15 minutes or 10 minutes here, bust out some calculus. Let's see, how are we going? I got to get to the actual derivative. All right, here's the derivative of the natural log. Now, the problem that we have is, I could just tell you the formula, but I don't like to do that. It's like, how in the world am I going to get a formula for the natural log? I want to take the derivative of a natural log of x with respect to x, and I want to figure out what is that equal to. We're going to introduce a new method, which is called implicit differentiation, which is the idea that if I have an equation like y equals natural log of x, can I rewrite that into its exponent form using properties? So this would be e to the y equals x. Is everybody okay with that? Now, by rewriting it that way, I now have a function I know how to take the derivative of. And you may be thinking, but wait a minute, there's not an x here, there's a y. Y is a function. If I called that g, would that make sense to you? If I said, what is the derivative of e to the g, what would you do? You would have to, what do you mean, take g? G is a function now.
Oh, wait, you do g prime.
Right? Why? Because if g is a function, if there is a function right there, what rule do you have to use? Chain rule. So y is really a hidden function. So when I do this problem, and I'm going to take the derivative of e to the y, I have to basically go, oh, wait a minute, y is a function. So I have to use chain rule on it. So the derivative would be the derivative of the inside. Now, usually when we do this, you kind of have to indicate, because we're doing something slightly different, that I am taking the derivative of both sides of an equation, which is different than me just taking a derivative of a single thing when you go it. And then I recognize that right here is a function, and so because it's a function, I have to use chain rule. So you start with the derivative of the inside. What's the derivative of y? Yeah, I don't like y prime. What do we call it? dy dx. Okay, so the derivative of the inside is dy dx. And then the derivative of the outside, what is the derivative of an e? Itself, right? So e to the y equals, now what's the derivative of x? 1. So we're like, okay, we get to there. So now I was trying to find basically the derivative of the natural log of x. I was trying to take the derivative of the y up here, right there, and figure that out and figure out what the derivative of the natural log is. So now when I have done this, now I can just solve for dy dx. So dy dx is equal to 1 over e to the y. Well, I'm not even going to do that. Now, what's different about this derivative is before, all of our derivatives were functions of x. Now I have a derivative that is a function of y. But I can fix that. I'm going to go right back to x. What is e to the y equal to? I'm going to just make it, I'm going to circle something way back up here. What is e to the y equal to? Oh, it's just x. So don't make it complicated. Don't try to be like, oh, I'm going to put some logs and blah, blah. It's right there. That's what I did at the very beginning. That's what our e to the y is equal to, so it becomes 1 over x. So the formula that you are going to memorize is that the derivative of a log is going to be 1 over x. Except I'm going to add one thing to this. What's the domain of a log? 0 to infinity. I have to say where x is greater than 0 for this problem. Okay. Yes?
So does the base of the log not affect?
It actually does. It does. This is only the derivative of the natural log. This is only the derivative of the natural log. Okay? All right, everybody good with that? Don't be packing up. I got 4 minutes. I'm gonna get this in. I'm going to skip example 7 because I just want to get the rules. Chain rule with the natural log. Here's your natural log of x is 1 over x when x is greater than 0. Notice if I put an absolute value inside, doesn't that just change the domain? Because what would be the domain of this natural log of absolute value of x? What does that change the domain to? Negative infinity to 0 and 0 to infinity. What's the domain of 1 over x? Everything but 0. So notice I have fixed the problem that I had about the domains being restricted on that. And then you can use chain rule on this. We're still doing derivative of the inside times derivative of the outside. It's pretty straightforward. I'm just going to do one of these to try to get you into the theme because I also want to do the derivatives of the logs that don't have a base of e. Like let's do the simple one, right here. I would say dy dx. What is the derivative of the inside x squared? 2x. What's the derivative of the natural log of g? 1 over x squared, because it's 1 over the g. And then at that, if you want to simplify, you could be like, oh, it's 2 over x. Okay? So same rules for chain rule are going to apply. All right? I'm going to leave you guys to do examples. Basically, whatever I'm skipping, you're going to do, okay, for homework to try it. All right, now what if the base is not e? What if the base is not e? All right? Do y'all remember the change of base formula? Change of base formula. If I have log base b of x, I want to change it to a natural log. Do you remember you do the natural log of the x and you divide by the natural log of the base? Okay? I am going to rewrite this conveniently. 1 over the natural log of the base times the natural log of x. And I'm going to point out that the base, when you know it, what is this actually if I know what b is? Think about when you're taking derivatives. If I know what b is, isn't this just a constant? So what do you know when you go to take the derivative of a constant? Well, but it's a constant times a function. If I take the derivative of a constant times a function, it's the... Do we not remember that rule? The derivative of k f of x with respect to x equals k f prime of x. So when my base is not e, the first thing I do is I change it so that it is a base e, and then I go to take my derivative, and the derivative just has an extra little constant in front of it because of the change of base formula. We typically do not always take the step of changing the base. We kind of just memorize that. You're like, oh, I changed the base, there's the extra constant, and you multiply it times the derivative of the natural log, which is 1 over x. So the big thing is to memorize the extra constant that gets added into that. So for example, here in example 10, right, I want to take the derivative. So I go, all right, start on the inside. What is the innermost function? 5 minus x to the fourth. What is the derivative of that innermost function? Negative 4x cubed. Okay? Now I work my way out. The next function is a log base 3. And I go, okay, I had to change the base. So my constant is going to be 1 over the natural log of 3. And then the derivative of the log, don't go yet, is 1 over the stuff. Right? And then I have one more thing to do before I can finish this derivative. I took the derivative of the inside. I took the derivative of the log. Now I got stuff squared. What's the derivative of stuff squared? 2 times that stuff, log base 3, 5 minus x to the fourth, all to the first, because I took the derivative. All right? Example 10. You can stop there. Anything that I have skipped, you need to do that comes before example 10. Okay?